The topic of my presentation is transforming semiconductor design using shift-left ESL methodologies. So as we are aware, since the inception of semiconductor industry 50 years back, there has been continuous enhancement on the multiple fronts, and due to which the chips are becoming continuously more and more powerful and more complex. So, designing such complex chips is not that easy, and the design methodologies have also continuously evolved to tackle the complexity of designing such complex chips. And historically, if we see these enhancements or this evolution in the chip design methodologies came in the form of raising the abstraction of chip design in different times. So like earlier we moved from component level design to the gate level design, and then from gate level to the RTL level design. And now maybe since last 2 decades, further like raising of abstraction is already happening. Several design activities are being conducted at a higher abstraction level. So this raising of abstraction today is happening on the multiple fronts. Like on one side we see that people are using the reusable IP blocks and designing the complete SoC using the reusable blocks coming from different vendors or from the different teams. And now further it's moving to the chiplet based designs as well. The another aspect is that we have to do the hardware and software co-design together. So we have to think at a slightly higher level where we actually design our complete product, defining what functionality goes into the hardware and what goes into the software. Further, like several design activities today are being performed using the high level languages like System C, C++, etc. So we can say that the traditional RTL to GDS flow today is not sufficient to design the complex chips of today, and several design activities are being performed at a higher abstraction level using the high level languages like C++, System C, Python, etc. And it actually enables us to perform several operations which are not feasible in the traditional RTL to GDS flow. So like we can develop a virtual prototype, which is a fast simulation model, which can be used for pre-silicon software development. So even before the chip is designed, the software team can actually start working with their software development activities. We can develop the simulation models which can be used for architecture analysis, like optimizing the power and performance, etc. Or for some algorithmic centric design, instead of handcrafting the RTL, we can use HLS. So like we create a design using C++ or System C, and using the HLS tool, we can actually generate the RTL out of it. The primary benefit we get is like while working at a higher abstraction level is a higher simulation speed. So it's feasible to like simulate at the SoC level or at the system level at a reasonably fast speed, which is typically not feasible when we are working at the very log level. So with all these activities being done at the higher abstraction level, lots of crucial decision making can be done quite early in the cycle. And if there are any flaws in the architecture or any flaws in the specification, those can be identified quite early and resolved quite early. So as I told, the primary benefit of moving to the higher abstraction is for achieving the faster simulation. So basically we can do the complete SoC level simulation or system level simulation along with the software at a reasonably high speed. So how do we achieve this faster simulation? So there are multiple concepts which are being used to design at this higher abstraction level. So like we do timing abstraction, we do interface abstraction, or we do functionality abstraction. So when we talk about timing abstraction, so primarily what we can do is when we are actually developing the simulation model at higher level, so we don't have to model the clocks. So we remove the clocks and we try to model the implementation in the loosely timed fashion, so that any activity that has to be performed in the future simulation time, for that we can do the mathematical calculation and schedule the events in future, or we can do the untimed implementation. So that way the timing abstraction, through this timing abstraction we can actually achieve the higher simulation speed. Another important part is the interface abstraction. So basically for any kind of data transfer for any communication protocols, instead of implementing at the pin level, so we do the implementation at the transaction levels using the function calls. So this has to be defined very carefully for various communication protocols. For the memory map buses, there is a standard called TLM 2.0 that we use for like register access or memory access in SOC. But when it comes to like other communication protocols, let's say UCI, LPDDR, PCI, HBM 3.0, or any other communication protocol which is being used for data transfer, so we have to define a custom like transaction level protocol for that, which has to be very carefully designed on the basis of like what is the use case for that particular specific model and what should be the abstraction level for that specific model. So, I mean the abstraction may actually range from, let's say, loosely timed model, which can be very fast, or it can go up to, let's say, cycle approximate transaction level model, or even the cycle accurate TLM model. So loosely timed models are primarily used for virtual prototyping, for like pre-silicon software development, etc. And we can have more accurate, let's say, I mean cycle approximate or cycle accurate transaction level models, which can be used for architecture exploration, performance optimization, or sometimes even for the RTL verification, etc. And the third part is the functionality abstraction. So we have to very carefully analyze like for what purpose our models is going to be used, and on the basis of that we actually take a call what portion of the functionality should be actually implemented and what can be abstracted away. So let's say if we are developing a virtual prototype for pre-silicon software development, so we just have to model that layer which is actually visible to the software, which is the register layer, and we don't have to worry about the underlying microarchitecture details, etc. So those things can be abstracted away. So this is one case study I'll talk about. So this is a virtual prototype of CoreV MCU which we recently developed. So CoreV MCU, it's a open source SoC from a industry alliance, Open Hardware. So Open Hardware Group is an industry alliance which is actually defining RISC-V processors and the open source SoC around the RISC-V processors. So we recently developed the virtual prototype of it. So this SoC have a RISC-V core. It has an embedded FPGA block. Apart from it, it has several like memory blocks and I mean general purpose peripherals like timers, etc. and various like external interfaces like UART, SPI, SDIO, camera interface, etc. So we developed a register accurate and loosely timed model for this complete SoC. The target use case is the pre-silicon software development. So the abstraction that we have chosen for it, like for timing abstraction, we actually removed the clocks and implemented it in a completely loosely timed fashion. For the interface abstraction part, so for the register access and the memory access, we use a standard TLM 2.0 socket. And for the other interfaces like UART, SPI, SDIO and camera interface, we actually defined the custom TLM protocol for this, mainly at the loosely timed abstraction level. And functionality wise, like we implemented only that functionality which is actually visible to the software. The CPU model, so we have taken a open source like instruction set simulator, and around that simulator we create a system C wrapper around it and attach the TLM 2.0 initiator socket so that it can be integrated into the system C environment. For eFPGA block, we just created a stub model because eFPGA does not have any IP functionality as of now. I mean the end customers actually can define their own functionality for it. So at that time they can develop the system C model for it and integrate into it. Yeah, so that's the current abstraction which we actually developed, and on this we are able to actually run the actual software stack which is available for this SoC. So we are able to run it on this virtual platform. In future, like we can further create different variants of the same SoC. So like we can create the more accurate model, more like I mean cycle accurate model or cycle approximate model of different interfaces, so that this can be used for architecture exploration purpose. Or we can even create some like adapters and transactors so that actually I mean we will be able to create a hybrid environment connecting it with the RTL simulation or the emulation so that it can be used for RTL verification as well. And this entire virtual platform we have developed using our own methodology, which we call CircuitSutra modeling methodology, which is a combination of, like, we have a CircuitSutra modeling library and virtual prototype quick start packages. So it's a small layer on top of System C, which is a collection of various convenience classes, utilities, etc., and a small model generator, which helps us to get started very quickly and develop the model very fast using it. So this is another case study, creating the custom transaction level protocol for various communication protocols. That's a very important activity in the modeling, and it has to be done very carefully for that. So I am explaining about this LPDDR5, like how we can model the LPDDR5 protocol at various abstraction level. So basically creating a custom TLM protocol for LPDDR5, and it can be useful for developing the model of LPDDR5 memory or LPDDR5 controller or LPDDR subsystem at various abstraction levels. So this TLM protocol can scale at different abstraction levels, like loosely timed TLM. So basically this abstraction level is similar to TLM 2.0 LTE abstraction, which is for the memory map bus protocols. So any read or write to the memory will be done using a single blocking function calls. So there will not be any intermediate like timing points. So the entire read transaction or the entire write transaction will be executed through a single function call. So it will not support the interleaving of the transactions as per the ZX protocol. The target use case for this is the virtual prototyping for pre-silicon software development. So that the simulation model for this will be very fast. It will not be accurate, but it will be very fast that way. And it's good enough for the use case when we are developing a model for virtual prototyping for the embedded software development. But for other use cases, so like we have to create more accurate model. It can go up to, let's say, cycle accurate transaction level model. It's not pin level. It is transaction level. But any read and write transactions will have to be implemented now through the multiple function calls. It cannot be a single function call, single blocking function calls. So like each function call will represent maybe one ZX command. Let's say activate 1, activate 2, pre-charge, refresh, write and read, etc. So the entire read transaction will be divided into multiple phases as per the ZX protocol. And for each command there will be the function call. And in this case, still we don't have a clock, but we can do the accurate timing calculation based on the clock intervals, based on the configuration of the model, what is the clock interval. Accordingly, the accurate timing points can be achieved at the boundary of these ZX commands, like activate 1, activate 2, pre-charge, read, write, etc. So that way we can have a more accurate kind of model, and it can actually even simulate the interleaving of transactions, various read transactions, write transactions as per the ZX protocol. So it becomes like quite accurate as per the ZX protocol and can be used for architecture exploration, etc. So let's say if you are actually implementing a LPDDR5 controller and you have to optimize your controller for performance or for other aspects. So in that case, this kind of like cycle accurate transaction level model of this LPDDR protocol will be required, ZX protocol will be required. Further, we can even have a more accurate model, which is like pin level model, which can be developed by creating some kind of adapters which convert from these function call to the pin, and maybe developing some RTL transactors so that it can be connected with the RTL simulation environment as well, creating the hybrid kind of setup which can be used for verification of RTL, or maybe creating more comprehensive like software driven test cases for verifying the entire subsystem, which could be a mix of like RTL and system C or C models, etc. So today these kind of methodologies are becoming very, very important for any new complex chips being designed. And today as we see in the industry, I mean, lots of work is happening in this domain of artificial intelligence and deep learning. So lots of new kind of SoCs are being designed for these use cases. So these kind of SoCs have very like specific requirements. Like, I mean, there is huge data processing, real-time data connectivity for the continuously coming data from the external sources. I mean, huge bandwidth is required for the data transfer off the chip and as well as inside the chip as well. Optimizing the power and performance is very important in most of these use cases. I mean, irrespective of whether this kind of chip is being used for the edge devices where there may not be a continuous power source, or whether it's being used in the data centers where the power consumption is becoming a huge cost there. And moreover, it has to, I mean, when you are conceptualizing such chip for these kind of applications, you have to ensure that it's going to work fine with the popular frameworks like PyTorch, TensorFlow, etc. I mean, in these kind of SoCs, we see most of the innovation that is happening is mainly in the compute and memory architecture, or even the combination of both of these. So, I mean, these shift-left methodologies which we talk about, these are very much relevant and very important for designing these kind of SoCs. So, let's say, I mean, virtual prototype. So, we can develop a virtual prototype, I mean, right in the beginning when you are conceptualizing your chip. I mean, at that stage, you can actually develop a virtual prototype, which is a fast simulation model, and you can actually validate that your chip architecture is going to work fine with various, I mean, software stacks, etc. And if you find any problems right in the beginning, you can change your architecture right in the beginning there. We can create the architecture models which will help you to optimize the power and performance for this. And for maybe more algorithmic centric design or for neural network which you want to accelerate inside the chip, I mean, instead of handcrafting the RTL, we can use the HLS. So you define the functionality using C, C++, etc. And for many of these, I mean, some open source C, C++ implementation might be already available, which can be taken as a starting point and maybe converted to the synthesizable code, and then using the HLS, we can generate the RTL out of it. Another important phenomena which is happening in the industry is this RISC-V, which is a new open source like processor architecture. So in this also, I mean, for the successful adoption of this RISC-V based method, I mean, systems in the industry, these shift-left methodologies again can play a very important role. So, I mean, the appropriate models for the RISC-V has to be created at a different abstraction levels. So, like if we see the other CPU models like ARM, so for ARM there is already a very robust like modeling ecosystem available. So, similar robust modeling ecosystem, I mean, will be required for RISC-V as well for the successful adoption of RISC-V in various kind of applications. So, like there are already some like open source RISC-V simulators, which are the fast untimed models like instruction set simulators. So, we can actually create a system C wrapper around it. So, at CircuitSutra, we created some system C wrapper around it so that these instruction set simulator can be actually integrated into the modeling flows. The architecture models can be created for the purpose of architecture exploration. So, there is some open source framework like Gem5 which is also being used, and apart from that also, like, I mean, there can be different methods for creating more like, I mean, more accurate like models for the processors which can be used for this architecture exploration. So, if we try to summarize the primary benefit of shift left, it helps to identify identification and resolution of your flaws in your new SoC architecture quite early in the cycle, like when you are just conceptualizing your chip. I mean, quite early in the cycle actually you can actually see whether it's going to meet the requirement of the target application, whether it's going to work seamlessly with the software stacks, etc. And if you find any flaws, you can actually, I mean, resolve it quite early in the cycle. Early software development is feasible. So, even before the RTL is designed and your chip is fabricated, the software team can actually start developing the software in parallel. So, it significantly reduces the cost and time to market for the next chip. So, effectively, and moreover, another important thing is, I mean, you can start engaging with your potential customers quite early in the cycle. I mean, right in the concept stage, actually, you can start talking to your customers and validate your concept on their applications, on their like workloads, etc. And further variants of, it also helps to roll out the further variants of the chip, quite easily and very fast. So, it significantly enhances the probability of the success of any new chip. So nowadays the chips are becoming so complex. Not all such chip endeavors actually succeed. So if we are using the effective methodologies right in the beginning, so it will significantly enhance the probability of the success. One of the challenges in the adoption of these methodologies is that it requires a very unique combination of skills, like which is a combination of computer science and semiconductors. So there are very limited number of professionals in the industry like who have the right kind of expertise, who understand the right modeling techniques, what is the right abstraction level for a specific use case. And other thing like System C is one of the standard which is being used for this methodologies. And the problem with System C is, it's a very versatile language. So in this you can create a variety of models. You can create a model which can run as fast as the real hardware, or you can create a model which can be actually as slow as the RTL or as accurate as the RTL. So unless you understand the specific techniques for developing the model for a specific target use case, you may end up developing a System C model which might not be meeting your exact requirement. So understanding, exact understanding of the use case and the specific abstraction for that use case becomes very important for this. So at CircuitSutra, we are trying to resolve these challenges. So we provide the SoC modeling services through which we set up the world-class modeling teams which work as the extension of the customer's team and execute these projects. So these teams can actually work remotely from CircuitSutra office or maybe on-site from the customer's site. We have a highly specialized System C training which helps the non-modeling engineers to become an expert in System C modeling. And this training actually goes beyond just teaching the System C language. It covers various modeling techniques, how to develop the models for the specific use cases also. Further, we have some reusable modeling methodology which we have developed over the period of time, which is a layer on top of System C, which is a collection of convenience classes and utilities and a model generator, which helps the customers to get started very quickly. So, we have the right kind of expertise in this shift left methodologies, and we are uniquely placed to work with, all the players in the semiconductor ecosystem. So, for the processor companies, we can develop the functional models or the instruction set simulators and integrate with the various simulation environments or integrate with the embedded tools, or even develop the cycle accurate models of their processors, which can be used for architecture exploration, etc. For IP companies, so we can enable your IPs with these advanced shift left methodologies by developing the System C models of your IPs and protocols, etc. at different abstraction levels. For SoC companies, we develop the virtual prototypes or the models for the architecture exploration. For the algorithmic companies, so we can accelerate your algorithms using HLS. So that way you have the complete flexibility that in different instances you can decide to use your algorithms in the software or inside the chip. So as a company, our mission is to accelerate the adoption of these shift left methodologies in the industry. So we are in the business for almost 18 years now. Since 2005, we are supporting the industry. We have an office in India, in Noida and Bangalore, and recently we incorporated the company in US, and we are in the process of setting up our team here in Santa Clara as well. So we have a world-class team of around 50 engineers, having a combined experience of more than 250 years, primarily focusing on the System C-based methodologies. We also got an outstanding contribution award from Accelera Systems Initiative for driving the Accelera standards in the Indian ecosystem. So perhaps today we are the only company which is 100% focused on these shift left methodologies based on System C and who understand all the aspects of these methodologies. Yeah, so that's all I have today.